R-CADT is pleased to invite you to participate in the course. Holistic Optimization of Electric and Gas Sectors. HI integrates its Optex, Optimization Expert System, with IBM technologies such as Watsonx, Decision Optimization and Plex Optimization Studio, and with GAM's General Algebraic Modeling Systems. This technological evolution, based on the power of computing, is changing the way we use artificial intelligence and mathematical programming, which is making previously learned concepts obsolete. HI operates as a knowledge factory in artificial intelligence and advanced mathematical modeling, focusing on artificial business management, autonomous AI that guarantees objective decisions. Artificial brains integrates organizational decisions based on neuroscience. Enterprise-wide optimization systems, EWOS, customized AI that integrates multi-problem model systems, and high-complexity mathematical models, traditional models that are part of our artificial brains. The course covers the following artificial intelligence methodologies: predictive artificial intelligence, machine learning, framework, advanced probabilistic models, neural networks, support vector machine, and hybrid methods, Kalman filter, decision-making artificial intelligence, framework, economics and optimization, large-scale optimization methodologies, mathematical programming with equilibrium constraints, parallel optimization, real-time autonomous distributed optimization, and artificial brains. Vision. The course covers two broad areas of applied mathematical programming: electricity systems and markets modeling, and implementation of enterprise-wide optimization systems. Both topics are addressed from HI's vision of multi-problem mathematical models, in which the development of computer solutions is oriented from the programming of algebraic formulas to the structuring of models, integrating the problems that make it up, as a Lego game. The student will learn about the main technologies for the implementation of mathematical programming algorithms and will learn to see them from this point of view, typical of Industry 4.0. But it is not a specialized course in algorithm implementation. Structure. The course is based on specialized academic activities aimed at training the participant in the main mathematical problems that must be solved in the strategic and tactical planning, operations scheduling, and process control of power systems and markets. The basic unit of the course is the virtual session with an average duration of 90 minutes each. To do this, the classes are recorded on videos by artificial intelligence. Classes are grouped into modules that cover the electricity supply chain and the commercial markets. After watching the videos, students must attend face-to-face virtual sessions, in which the course teacher will clarify existing doubts. 2 conversations are held monthly. Students should submit their questions in advance. Aimed at professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and/or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and/or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives: training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives: Learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variables. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Electrical industries. Advanced analytics and optimization solutions across the enterprise. The image, produced by IBM, presents opportunities for optimization along the electricity supply chain. At the origin of mathematical models in computers, starting in 1947, decision support systems, which represent the optimization system of an electric company, were visualized as composed of multiple mathematical problems, one for each line of the diagram, which are operated individually and communicated sequentially by humans. This way of operating produces solutions close to the optimal, but not optimal, because they generally have no feedback. The current technological revolution completely changes this approach. Today, electricity business optimization can be visualized as a single supermodel, composed of submodels, which in turn are made up of mathematical problems, one for each line of the table, which are solved by running in parallel, autonomously, communicating with each other, and managed by a mathematical artificial intelligence, produced by a generative artificial intelligence. Hierarchical coordination of planning tools. It is traditional to organize decisions hierarchically into strategic, tactical and operational. The operational decisions are divided into the scheduling and advanced optimal control. However, due to the technological progress generated by Industry 4.0, mainly in relation to smart metering systems, nowadays we can talk about a new type of online optimization modeling, real-time distributed optimization. From the point of view of mathematical modeling, hierarchical levels are intertwined and coordinated through the boundary conditions in time, and common modeling that can be shared. The modeling strategy of HI is that all models of a decision support system can communicate with each other. Considering the vision of large-scale optimization, which can have multiple points of view, HI developed the multi-Benders decomposition (MBD) algorithm to emulate the coordination of multiple points of view, just as the human brain does, following the studies carried out by Jeff Hawkins, summarized in his book, 1,000 Brains. Power enterprise-wide optimization system integrates mathematical models for each of electricity's supply chain links, so that supply chain planning is managed with a holistic view. Construction of artificial brains. The methodology for building an artificial brain follows a formal modular process, which HI calls structured mathematical modeling. First, all mathematical equations, and their components, are stored in a relational database, part of an artificial hippocampus, which can be handled using SQL, standard query language. This implies an open and standardized structure, which is not common in mathematical modeling. Sets of constraints form problems, called by HI, mathematical artificial neurons, and sets of problems form models, and a set of models forms an artificial hypothalamus, which is linked to the corresponding artificial cortex, a network of mathematical artificial neurons, and the artificial hippocampus, memory, which stores, in addition to mathematical formulations, the history of all model runs. From the concept of enterprise optimization, it evolved towards enterprise-wide optimization, which implies expanding the coverage of the decision support system, which HI calls enterprise-wide optimization systems. Visually, it is easy to see the evolution of the IBP concept to AWO, which covers all operational functions of an industrial organization. This leads us to two problems that must be solved from a computational point of view. If traditional approaches are used, many programmers are required to generate all the source code needed to develop and coordinate all models, and it takes a lot of computational power to solve the built-in problem. To solve this situation, HI has developed OptEx, Optimization Expert System, a generative artificial intelligence, which is responsible for producing all the source code required by an artificial brain, using large-scale optimization methodologies to solve complex high-dimensional problems. Electricity system and wholesale market mathematical models. Make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. Traditionally, the optimization models in the electricity sector consider individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences with the state-of-the-art modeling, provided by high-power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. Three types of connectivity of the generation system and the transmission power grid are considered. Ideal single node, ideal dispatch ignoring the transmission system. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible to use the connectivity based on operational area //app. Blaster online. com/speech low/changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection of electricity and water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. The central model of high power is the standard representation of the electricity and gas supply chains. These equations give rise to variations of the model according to the techno-economic concepts that support a specific modeling. There are at least 4 types of economic models to represent the electricity and gas market. Economic perfect dispatch, EED. Economic regulated dispatch, ERD. Nash-Carnot equilibrium dispatch, NCD, and unit commitment, UC. The EED is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. EED and the UC models optimize the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. The differences between these two models are the detail of modeling. EDD is oriented to planning and UC to real dispatch. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. Nash-Carnot equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence with their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant market power of agents. 4 models are considered fundamental to support the strategic, tactical and operational decisions of an agent that operates generation plants. The diagram presents the design of an integrated set of mathematical models to support the decision-making of a generator agent. Electricity dispatch and financial analysis. Integration dispatch models with assets liabilities management, ALM, financial models including risk management, to perform analysis of the financial impact of decisions. The main applications are the valuation of income and expenses of investment projects, energy installations, and valuation of energy companies, and integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Electricity supply chain design and risk management, associated with strategic planning decisions related to resilient design of supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It may include risk management and financial planning. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or no bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in long-term market, spot market, and secondary markets. The result of a risk analysis is the definition of Pareto curves of risk versus expected revenue, based on which the decision maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High power man can be implemented following the principles of PHM, prognostics health management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High power has been used by ISO, in Peru, and Market Supervisor, in Colombia, for planning and decision-making purposes. High power includes some predictive analytics models. Spot price modeling. The prediction of spot prices of the energy market is fundamental for the decisions made by an agent that participates in that market, whether buyer or seller, generator, trader, or distributor of energy. This is because the decision maker requires that the model's results that produce spot prices be used in other mathematical prescriptive models. The mathematical models to be used depend on the planning period, short, medium or long term, and the type of market considering the dispatch of the plants, by mathematical model, or by market agents offers in a free market. In free markets the situation is complex since the law of price formation cannot always be explained based on mathematical rules, explicit, clear and universal, that may integrate a mathematical model. Synthetic generation renewable energy sources. For the generation of synthetic scenarios of climate variables, there are two requirements: short-term, hours, days, and medium/long-term, weeks, months. Specific short-term models must be built for each renewable source. For the medium and long-term, there are three alternatives to generate synthetic scenarios. Synthetic statistical model for the generation of climatic variables, firing Methodologies type. Generate synthetic series of climatic variables based on the mixture of historical series. Generate synthetic series based on the historical series having the ENSO series, El Niño Southern Oscillation, as an instrumental variable. Projected short-term hydrological contributions using variations and enhancements of Kalman filter. All Power L models share the same data model, input and output, in such a way that communication between models is direct. In the same way all models make up the artificial hypothalamus of the wholesale market of the electricity sector. Smart grids optimization models. In a regulated environment, generation, transmission, and distribution are operated by a vertically integrated enterprise, usually a state-owned, which has a monopoly on the supply of electricity. Conversely, in a deregulated environment, different parts of the electricity grid are owned and operated by different actors and electricity markets provide a platform that fosters competition among participants. As each smart grid is, it requires a specific decision support system that allows the operator to interact with the entire electrical system. High-SGO provides all the analytical elements necessary to configure the specific DSS that each case requires. High-SGO is composed of forecasting models and optimization models aimed at supporting the decision-making of electric agent smart grids, optimization of the economic and technical aspects related to smart grids and electricity companies. Demand response for buildings and housing, demand response, optimization of energy management in facilities, such as universities, shopping centers, and industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Forecast of demand energy. Demand projections per years, months, weeks, days, hours. High-SGO is integrated by the following optimization models. Economic dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the dispatch of the electrical load in real time, or in the short term. Smart grid configuration, optimizing the network topology, it considers voltage control, configuration of feeders, location or activation or reallocation of electrical assets, like transformers, capacitors, and phase balancing. Smart grid design, optimization of the design or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and or sell electricity, in a long, medium and short-term market, one day in advance or the day of dispatch. Industrial energy efficiency. The technical economic viability of energy storage coupled with the proliferation of energy technologies based on renewable energy sources has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. In practice, all industrial companies can be agents that interact in the electricity market acting as co-generators and carry out commercial activities and transactions. This, together with the industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and high-SGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. High-power and high-SGO integrate the models and information systems around a common data model, allowing models to be connected automatically through the database or through RAM memory, integrating them as an artificial hypothalamus for an electricity company of wide coverage. The course director is the founder and scientific director of R-CADT. Engineer Velasquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated more than 50 years solving real-world problems, doing engineering consulting using mathematical models. This is the technology transfer that those attending the course will receive. The table summarizes the plan of topics to be discussed. Continuation of the previous table. RCADT and/or high issues a certificate signed by the scientific coordinator, for which the student must participate in at least 20 conversation sessions. R-CADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.